Hi, guys. How you guys doing this morning? Can't tell if that's better or worse. Okay. All right, we'll see. Is that better? No, this is better. Okay. Trying to figure out the lighting here. All right. So we'll talk administrative stuff for a few minutes while we're waiting for people to trickle into the class. Don't forget, homework is due tonight. So homework on chapter 2.5, 2.6, and 4.1, that's due by midnight tonight. Technically, Canvas says it's 11:59, so keep that in mind. So that's today. And then also our quiz on those same chapters, 2.5, 2.6, and 4.1 will open up today availability wise at 3 o'clock. Okay, so 3 o'clock today, the quiz is going to open. You guys will have 24-hour window in which to take it, but once you start it, you have to complete it. Okay, so keep that in mind. It's a 45-minute quiz, but what that means is you have 30 minutes to actually do the math and 15 minutes to download, print it out, work on it, take a picture, upload it, or download it, work on it, whatever, however you want to do it. If you do it on a separate piece of paper, you don't have to print it. Make sure you write the question out, okay, and then write out your answers. If you guys are looking for the solutions for the quiz from last week, I posted the quiz solutions on last week's module. It's like listed right underneath where the quiz was posted. Okay, so keep all that in mind. That's all stuff coming up today. Okay, all right, so let's go ahead. Yesterday we finished up chapter 4.1. I posted the lecture example solutions for 4.1 on our Canvas page. And today we're gonna finish up part 1 of 4.2 and then start part 2 of 4.2. They're all related. Remember, there's only one homework assignment for 4.2. Okay, I didn't break that into 2 parts. All right, so let's go ahead and remember where we are. So 4.2 was all about basically taking a function, right, a non-polynomial function like e to the x, sine, whatever, and we're going to approximate it using a polynomial, okay? And why do we want to do that? Why do we care? And that is because these complex functions like exponentials, logs, sine, trig functions in general, all of these things are complex functions that we use to describe the world around us. They describe the natural world. And they can get very, very complex. The examples we're using are relatively simple, although maybe it doesn't seem like it, but just a plain old e to the x or a sine function, say, for example, it's not as complicated as, you know, long strings of these things combined together. And we need a way to analyze them that's going to break it down into parts so that we can write computer programs about them, to optimize the programs so we can do a lot of processing, computer processing on them, so that we can actually, you know, take derivatives easily, take integrals easily, do other kinds of analysis, you know, differential equations on them. So we need a way to be able to break these things down. So we're representing these complex functions using polynomials. Polynomials are easy, right? I mean, like I can take a derivative, I can integrate just using the power rule with a polynomial. Okay, so how we convert a function to a polynomial is what we're learning. Okay, so yesterday we talked about a Taylor polynomial, right? So a Taylor polynomial is basically it's a function that's centered at a particular value, whatever a is, you know, any number, any real number, centered in its nth order, so that's our highest degree term. We're going to expand on this idea today about the polynomials. And Maclaurin is just like Taylor, only we're centering it at 0. 0 is important enough that it gets its own polynomial name, because we want to be able to center it there. So let's go ahead. I'm going to take out this is my lecture examples for 4.2 part 1, and I'm going to jump right in. So this is example 2. And what we want to do is find the Taylor series for the function f of x equals sine of x. And we're going to center it at pi over 2. Okay, so we're centering it at a value other than 0, which means we're doing Taylor instead of Maclaurin. And we're going to use the first 2 non-zero terms to estimate the sine of 1.5. Now, I just want to call your attention, oops, sorry. I just want to call your attention. So we're looking at the sine of 1.5. Remember, all angles are in radians. So when you give me answers for angles, whatever problem that you're working on, make sure it's not in degrees. We're not going to accept degrees anymore. I accepted it on the quiz one, but now I'm going to start taking points off because that's what will happen on the final exam. So let's take a look. We can do this in our head too, but I just want to show it to you. So here's pi divided by 2. You know, pi is like roughly 3.13. It's roughly 3 divided by 2. So it's like roughly 1.5. So pi over 2 is like 1.57. It goes on and on, right? So we're going to estimate 1.5, sine of 1.5. So it's like basically, that's why we're centering it at pi over 2, because pi over 2 is really close to 1.5. Okay, that's why we're not using a Maclaurin, because Maclaurin is going to be centering it at 0. We want to center it at 1.5. Remember what we talked about before, that our approximations can get really, really accurate, can become really, really good if the number that we're looking to estimate is where our polynomial is centered, right? So we're looking to estimate sine of 1.5. So we're going to center it really close to 1.5. Right? If I centered my polynomial approximation at 0, my estimate of sine of 1.5 would not be as good. Okay, so we reduce the error by focusing our attention and our polynomial in the same spot. Okay, so enough about that. Let's go ahead and jump right into our example here. Okay, so the first thing that we need to do, we want to actually compare. We're gonna we'll do this out on our calculator in a little bit, just so we can see how good our estimate is. So the first thing we need to do is we have to come up with our derivatives, and we have to evaluate it at pi over 2. So let's make a little table. So here are my derivatives. And then this is going to be x equals a, which is equal to pi over 2. So we're going to evaluate it there. So my function, this is my 0th derivative. We don't tend to write 0th. It's just our function is equal to sine of x. And then my function evaluated at pi over 2. So this is sine of pi over 2. Make sure that you're up on these things. Sine of pi over 2 is equal to 1. Okay, so our first derivative of the sine function is cosine of x. So our first derivative evaluated at pi over 2 is cosine of pi over 2. This is equal to 0. Okay. Second derivative, I'm going to do several. They say the first 2 non-zero terms. And usually with trig functions, we have, depending on the value, especially like pi over 2, it's right along the unit circle. We're going to get, combinations of 1s and 0s. So they're not telling us what order to use. They're telling us, go as far out as you can to get the first 2 or 3 or however many non-zero terms. So second derivative is going to be derivative of the cosine, right? So this is minus the sine of x. Second derivative of pi over 2, so this is equal to minus the sine of pi over 2. Sine of pi over 2 is 1 minus the sine. It's going to make it minus 1. And I want to do this out just so you can see. So my third derivative, right? So sine is cosine, but minus. That's going to be minus cosine of x equals 0. And I'm going to do this because we're going to actually talk about this in a minute. So cosine is minus the sine. Minus times minus becomes positive sine. So by the fourth derivative, we've looped back around again. This is what happens with trig functions. They have an infinite number of derivatives. I can do this forever, right? But there's a pattern. So I've got the 0th through the third derivatives, and then functionally I start off again. It's going to look just like the 0th through the third derivatives over and over again. Okay, so after the fourth, we might as well just go ahead and do it while we're here. So this is equal to sine of pi over 2, which is equal to 1. Okay, so we've got our derivatives. So this thing, derivatives cycle around. Okay, so we basically get this repetition of values of functions, like what our derivatives are. It happens with trig. Okay, so I'm going to write out, I don't know what the order is yet, but I'm going to just start writing out what my Taylor function looks like. Remember, our Taylor function is going to be f of a plus f prime of a divided by 1 factorial, which is just 1, times x minus a to the 1 plus f double prime of a over 2 factorial x minus a squared. Plus we're going to go out a couple terms of a 3 factorial. See, this is third derivative 3 factorial x minus a cubed right? And then we'll just go out to the fourth here of a 4 factorial x minus a to the fourth, plus so on and so forth. Okay, so this is like our individual terms for our Taylor. Okay, and now what I'm going to do is I'm going to fill these in. My a is equal to pi over 2, so I'm going to fill in these values.
Oh, shoot.
I think somebody's needs to mute themselves. So my f of a, my function evaluated at a, is equal to 1. I'm just going to fill them all in, and then we'll knock off the 0 terms in a minute. So my first derivative, right, is equal to 0 times x minus pi over 2 to the 1, plus my second derivative is equal to minus 1, minus 1 all over 2 factorial x minus pi over 2 squared. I'm gonna do out all of these terms here, and then we'll just take the first couple. But let's do it out so you can see what I'm doing here. So that's my second derivative, right? X minus pi over 2. So my a is pi over 2, right? So that's why I'm plugging it in there. And then my third derivative, I'm going here, is 0 x minus pi over 2 cubed. This is all over 3 factorial, plus my fourth derivative, which is equal to 1, 4 factorial. Sorry, you can't see that. 4 factorial x minus pi over 2 to the fourth, and so on and so on. Okay, so I just wanted you to see what we were doing. We're plugging in these values. I also want you to know, look, we were estimating the function sine of x, right? This is my polynomial right here. Okay, it has my a value. It's in polynomial form. There is in no way, shape, or form a sine of x anywhere in here. Okay, I've already evaluated that. That came out in my function and my derivatives. Okay, sine of, x, cosine of x, minus sine of x, all those things evaluated at a. We're going to get a number. So be very careful. I often see this as a mistake people make. They put, like, somehow they kind of convince themselves they need to put, like, the function, somehow sine of x needs to go in the polynomial. This is a polynomial. It does not contain our original function, okay? Except that these portions here that represent the derivative evaluated at our a value, okay? So that's it, but that's a number. When you have a derivative evaluated at a number, that's a number, okay? So it's like our slope of our tangent line. Okay, so now let's go ahead and evaluate this. So this is going to be, the question said use the first 2 non-zero terms. So the first 2 non-zero terms, this is non-zero, that's 0, this is non-zero. So, and then I don't have to worry about the next 2 terms because they said only take the first 2. So I'm going to look at 1 minus, right? This is 1 over 2, 2 factorial is 2, x minus pi over 2 squared. And this actually ends up being a second order pi over 2. They told me to do the first 2. If they said the first 3 non-zero terms, I would choose this one, and this one. Okay, so it depends on what you're being asked to do in the problem. So I'm just going to put a box around it. So this is our first 2 non-zero terms. Okay. All right, so now they said, the question says, use this, our polynomial here, to take a look at, use it to estimate, use our polynomial to estimate the sine of 1.5. So this is like saying, this is here sine of x. So this means x is equal to 1.5. So what that means is I'm going to take my polynomial, I'm going to say my second degree polynomial, I'm going to go 1.5 print here, like that. And I'm going to use it. So I'm going to take this polynomial, everywhere I see an x, I'm going to plug in a 1.5. Okay, so I'm going to go 1 minus 1/2, 1.5 minus pi over 2 squared. Okay, and I do it on my calculator. Use the pi button, right? 1.5 minus pi divided by 2, parentheses, watch your order of operations, square it, divide by 2, subtract it from 1. When I do this, I get 0.997493. Okay, and just for reference too, when I did on my calculator, the sine of 1.5, make sure you check your mode. You should be in radian mode on your calculator. if you do this in degree mode, you're going to get garbage. Sine of 1.5 is going to look like 0.9974986. So 0.99749, 0.99749. And so then we basically start to, bump off like right about here. So it's not so bad. We went 1, 2, 3, 4, 5 places after the decimal. Okay. So just even with the second order polynomial, we're operating at, 5 decimal places out, which for correctness is pretty good, right? So imagine if we went out like the first, say, 100 non-zero terms, our estimation, we would be going way out in terms of our error. Our error would be really, really, really small, right? So the more terms you add, the higher your order, the better your approximation. Certainly when your polynomial is centered close to where you're evaluating it, which it is. 1.5 is close to pi over 2, okay? Okay, so that's 4.2 part 1, okay? 4.2 part 2 is very similar to 4.2 part 1. I'll let you guys finish writing this, and I'll scan this in and upload the solutions for this part, and we'll see how we do on part 2 later. Hopefully I can scan them both in. Okay, so this is a Taylor polynomial, right, where it's basically a second order polynomial, right? But I just want to keep emphasizing the point that I do not have a sine function anywhere in my polynomial. My polynomial is just a function of x, right? It's like, x squared, x cubed, x whatever, third, fourth, fifth, however higher order needs to go, okay? Okay, so let's talk about 4.2 part 2. Okay, so, it's the same thing. We're still dealing with, approximations. We're going to be doing that for the whole of chapter 4. So we're going to take the idea of a polynomial, and like a polynomial, we say, and remember how we rewrote it. So instead of starting with the highest degree term down to the smallest, we went from the smallest to the highest, right? Well, now think about it like this. And I said, okay, so it's a second order polynomial, right? Or a third order or fourth order. So our highest degree term was 2 or 3 or 4, depending on what order it was. Okay, well, now imagine a polynomial that has an infinite number of terms. Okay, so if we have a polynomial that we just go plus dot 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 and it goes on forever, okay, we don't call it a polynomial anymore, we call it a power series. Okay, series because I can represent it with an algorithm, okay, a sum, an infinite sum, but a power, we call it a power series because it has terms, x raised to a power, okay? So it's a polynomial with an infinite number of terms. So let's write that down. So a power series, that's an easy, power series. Okay, so we're gonna call a power series centered at A. So just like we have been doing, this is a formal algebraic expression, okay? It's, kind of a fancy way of saying it's an infinite polynomial. It's a polynomial with an infinite number of terms. You can think of it this as a polynomial So if I say I've got my Taylor series and I'm going to do the first 2 or 3 non-zero terms, that means that I'm doing a third order partial sum of my Taylor series, right? So remember we said partial sum was, I've got a polynomial, I've got 5 terms, but I only talk about the first 2. That's maybe second order or first order partial sum. I'm only partially summing up all of that stuff. Well, if it's an infinite polynomial, we can't sit here and write it all out, right? So if I only represent the first handful of terms, that's what we call a partial sum. So that's why we were belaboring those terms. All right, so power series, let's write it out in math. So now we've got our sum, k equals 0. Now instead of going to n, I'm going to go up to infinity. Remember, I warned you we were going to go up to infinity at some point. So my coefficient, x minus a to the k. So it looks just like what we have been doing, right? And c sub k is our constants. And we're going to be deriving c sub k. That's how we're going to actually make our Taylor or Maclaurin series related to the function that we're trying to approximate. We're going to derive those ourselves, but let's just write it in terms of constants. So we've got our 0th term. So it looks just like what we have been doing, right? So I've got 2x minus a squared. Now notice I'm not dividing by factorial because that's all incorporated in my constant, right? The formula for our constants we're going to talk about in just a minute. C sub 3, x minus a cubed plus, and so on and so forth, right? Look, goes on forever, right? We're not going to sit here all day and write it all out because we can't. All right, so let's talk about specifically, we're going to talk about a Taylor series. Very similar to a Taylor polynomial, right? Except we have an infinite number of terms. So a Taylor series of a function f of x. F of x is what we're representing with our polynomial. Taylor series of a function f of x. And f of x itself is what we call infinitely differentiable. So f of x is infinitely differentiable, right? Which means like e of x, right? Or sine of x, I can sit here all day and never run out of derivatives, okay? So I can take an infinite number of derivatives. There's a whole class of functions that we're using right now that we're going to represent that have an infinite number of derivatives. Is infinitely differentiable and is centered at A, okay? So let's write out our Taylor. So we now write, we don't write the superscript anymore because it's an infinite superscript. If I did, I would write it like this. Oops, sorry. Sometimes like some books will write it out. Okay, so it's not a J that I'm trying to emphasize, it's a semicolon. So this is our infinite Taylor, this is a Taylor series because I have an infinite number of terms. It's a function of x, semicolon, and it's centered at A. And that's equal to, we've got our sum, I'll write it in summation form, just so you can start getting accustomed to the summation form. And then we'll write out the first handful of terms. So our kth derivative evaluated at A divided by k factorial, x minus a to the k. So this is just like what we have been doing with our polynomial, only now we go on forever. Okay, so this thing looks like what we did before, f of a plus f prime of a, x minus a, and I'll write it to the 1, just so you can see, plus f double prime divided by 2 factorial and so on and so forth. It doesn't have an ending, right? It just keeps on going. Okay, so a Taylor series centered at A. So when A equals 0, this is called a Maclaurin series. Same thing, only A is equal to 0. Okay, like I said, 0 is an important enough location. A lot of things happen around 0 in functions, so it gets its own name. Okay, so we say that the nth order Taylor polynomial, which is what we did yesterday, equal to the nth order, whoops, sorry, you can't see what I'm writing, nth order partial sum of the Taylor series. So the nth order Taylor polynomial, when we say, oh, do the third order Taylor polynomial, that's the partial sum, the third order partial sum of our Taylor series. Okay, so imagine Taylor series is an infinite series. If I only want the, if I want a third order, that's a partial sum of an infinite series. Okay. All right, so my lecture examples. Okay, so we'll start taking a look at some of our lecture examples for this. Same methodology that we have been doing. Okay, all right. So now we've got f of x equals sine of x, again, like we just did. We're going to use the Maclaurin series now. So the Maclaurin series means a is equal to 0 to look at the sine of x. Use the first two non-zero terms to estimate the sine of 0.1. Remember, this is in radians. And we're going to compare that to our estimate of sine of 1.5. Okay. And I'm going to use the sine of 1.5, do the sine of 1.5. If I do 1.5, when I do the Maclaurin series, we're going to see that it's not such a great estimate. Okay, so let's do this. So I'm going to go TF of x. Now watch, I don't write the a anymore because a is equal to 0. I'm just going to write this down, k equals 0. And I'm going to go up to infinity. So k of 0 now, k factorial, x to the k, just to kind of remind myself like what I need to do. Okay. And I always like to write this out just so I remember. And so on and so forth. That helps me remember what I need to do and like what are my steps. Okay, so then the first thing I need to do is come up with our table. I know we just did this, but let's go ahead and be good about it. Derivatives, x equals a, which is equal to 0. So our function, our 0th derivative, is sine of x. F of 0 equals sine of 0. So now the sine of 0, remember, is different than the sine of pi over 2. So this is equal to 0. So this is on our unit circle. Sine of 0 is equal to 0. Our first derivative is equal to cosine. Our cosine is equal to 1. Second derivative minus the sine minus the sine of 0 is equal to 0. Third derivative is minus, from here, cosine. Third derivative at 0 is minus the cosine of 0, right? So minus 1. Okay, so I've already got, like this had used the first two non-zero terms. I could go, I'll do the next couple. I'm going to get in the habit of doing a couple more derivatives than I think I need, because ultimately we're going to need to come up with a formula to generalize these derivatives. Okay, so I'm just going to come up with a couple more just so I can kind of think about what's happening here. Just to get in that habit. We're not doing it yet, but we're getting our minds ready to think about it. So this is going to be sine of x again, f to the 4th of 0 is equal to, I know what's happening here, 0, f to the 5th, cosine of x, f to the 5th at 0 is cosine of 0, which is equal to 1. Okay, so but these are the ones that I'm going to be using because they said the first two non-zero terms. Okay, but like I said, get in the habit of going a couple beyond what you need, because ultimately you're going to need to come up with a formula. Okay, so I'll put a little line underneath the ones that we're going to use. I'm going to use this one, and I'm going to use this one, right? The first two, because they said the first two non-zero terms. Okay, they didn't say give me the second order Taylor or Maclaurin series for this, but they said do the first two non-zero terms, which is actually going to put us at a third order partial sum. Okay, so let's go ahead and write it out. Okay, so TF, and I'm going to do this first of x, right? So I'm going to fill in my blanks here. So my we'll write it all out first, and then so I've got a 0 plus. Give me a second. So 0 plus my first derivative at 0 is 1 times x plus my second derivative at 0. I'm going to write them all out the zeros, and then we'll cancel out what we don't need, x squared, plus my third derivative, which is equal to minus 1, 3 factorial x cubed, and then I'm going to leave it like that. Okay, with a, and now when you want to represent this to plus dot dot dot, okay, we will accept plus dot dot dot. Okay, on the exams, on the final exams, they'll say write it in summation form, which is come up with a generalized formula for it, or you can write it as plus dot dot dot. Maybe they'll ask you for like the first 5 terms, say for example, and then plus dot dot dot. But right now we're just going to do it like this. Okay, so now I can say what I'm looking at is scroll up just a little bit. So let's get rid of our zeros. So the zeros, the things I don't need, I'm not going to use that one, and I'm not going to use that one. I'm going to leave things in terms of factorial just for now. So I've got 1 times x, that's x, minus x cubed over 3 factorial. Okay, plus dot dot dot. Okay, so I can leave it like that. But they said just the first couple terms, so I'm going to go like this. Okay, so this is my Maclaurin Series 4 f of x equals sine of x. Okay, now notice there's no sine of x anywhere in sight, no trig functions. It's just a polynomial, right? The coefficient here is 1/6, the coefficient here is 1. I mean, I can take derivatives, I can take integrals, whatever. We're going to do that later in later sections. Okay, so now what they want us to do is they want to use this to estimate, right, sine of 0.1. So I'm going to go 0.1, right? So everywhere I see an x, I'm going to plug in a 0.1. So 0.1 minus 0.1, oops, sorry, cubed all over 3 factorial. And that's going to give me, what did I get when I did that? Let's see, 0.0998333. Okay, so this is, sorry, estimating sine of 0.1, which when I did it on my calculator, I got 0.0998334. Oops, sorry, I'm running out of space, 6. Okay, so 0.0998333, and then it bombs out here, like we have an error here, right? That's where we start to diverge. Okay, now let's use this to estimate sine of 1.5. So, right, so here notice that the thing I'm trying to estimate is close to where I've centered it, right? Let's write that down. So 0.1 is close to A, x equals A, which is 0, close to centered value, right? So let's do a value that's farther away from where we centered it. So I'm going to go t f of 1.5 is equal to, everywhere I see an x, I'm going to plug in a 1.5. 1.5 minus 1.5 cubed all over 3 factorial. And that's going to equal to, when I did it, I got 0.9373. Now remember, on a calculator, right, the sine of 1.5 was equal to 0.997494. Right, so when we did this just a few minutes ago, right, when we did this, we centered it at pi over 2 because that's close to 1.5. We got 0.9974, right? It was pretty close to the calculator estimate. But look at what we're getting now, 0.93. I mean, I'm like, it seems trivial, right? I mean, it's like 0.9, it's close, but I mean, like, I wouldn't want to launch a rocket to, you know, a far off place or even to a close place, you know, with this kind of an error, right? I'm only accurate up to the first number after the decimal, and then it bombs out. So that's like an example of why we want to center our polynomials near where we want to look for values. Okay, so think about that. So 1.5 is not close to A, which is equal to 0. Should use Taylor with A equals pi over 2, since it's closer to 1.5 in value. So this is an example, right? Because look, right, that's where our error is. The error, it's a big error. Okay, I would consider that a big error. It's not like ginormous error. It's not like an order of magnitude error, but it's, you know, I mean, we're in the right ballpark, but it's still a pretty good size error. Okay, so that's why we want to center it. Whew. Okay, you guys good with that? I'll give you guys a minute to finish writing that part, and then we'll talk. Okay. All right. Okay, so let's start thinking about representing things as formulas. We're going to keep going back. We're going to keep practicing this stuff, but I also want to take you and let's take a step back and start thinking about how we're going to generalize this. So Okay. As we go along, it becomes a big discussion about how do we generalize our derivatives into formulas. So I'm always going to be trying to call your attention to that. So let's think about if our function is equal to the sine of x, right? I said it loops around, right? So my first derivative is cosine. My second derivative is equal to minus the sine. My third derivative is equal to minus the cosine of x. And my fourth derivative is equal to, finally going to loop back to sine of x. So it looped back around, right? So when x is equal to 0, right, when a equals 0, right? So on our Maclaurin, let's talk about, like, this is our Maclaurin. Okay, on our Maclaurin series, right? So it loops, right? And then you can imagine, like, I can just keep looping back and forth. So I can kind of come up with a formula for it. So at x equals 0 on our Maclaurin, my coefficients also have a repeating pattern. We saw this when we just did this example, but let's go ahead and do it. So if I plug in, right, I've got sine of 0. Sine of 0 is equal to 0. Cosine of 0 is equal to 1. Sine of 0 is equal to 0, minus 1, 0. And then because this thing loops back up to the beginning again, right, we're going to get this same pattern. So 0, minus 1, right, and so on and so forth. This whole thing becomes our pattern, right? This is what we're dealing with here. Okay, so our Maclaurin has a pattern. Okay, so using these coefficients in our Maclaurin polynomial, right, our series. Okay, so I'm going to apply these coefficients in there. What am I going to get? Right, I'm going to get 0 plus 1 times x plus 0 x squared, right? Plus, I didn't do the divided by 2 factorial because the 0 is going to dominate, plus minus 1 over 3 factorial x cubed plus 0 times 4 plus, right, x to the 5th over 5 factorial. There's a positive 1 here, plus 0 times x to the 6th, right? I'm not putting in the divide by 6 factorial because the 0 is going to bomb it out, right? And now again, so I'm going to go, so I'm doing like 0, 1, 0, minus 1, 0, 1, 0, minus 1, right? X to the 7th over 7 factorial plus 0, 1, 0, minus 1, so on and so forth. So I'm using this to try to generate some kind of a pattern, right? So let's write this out. Is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, you can imagine, right? Look, these are all odd. This is 1, 3, 5, 7. This is going to be 9, right? This is the next one up. And so on and so forth, right? So this is our sine function, our Maclaurin for the sine function. Okay, we're trying to show this to you because ultimately what we want you to do is start recognizing these patterns. I don't expect you to memorize this right now, okay, but as you go along, you're going to be doing a lot of sine functions, or you're going to be given a polynomial like this as you go, especially in later engineering classes, and then you're going to be able to say, oh yeah, oh, that looks like the sine, Maclaurin for the sine, right? So we're trying to help you start to think in terms of patterns so that you can recognize these polynomials, because these ultimately we're gonna label them as fundamental Maclaurin polynomials. We're gonna get to that, but we're starting to kind of get you to think about that ahead of time. Okay, so let's talk about sine and cosine as Maclaurin. So Maclaurin polynomials, right, or series, right? So a partial sum or the whole series. So the sine of x is an odd function. Okay, now I don't mean, oh, that's an odd function. I mean, it's an odd function, as in, remember from high school, I know algebra 2 or trig, I don't know when you would have covered it, but an odd function has specific properties, odd and even functions, right? So an odd function, right, if I do f of minus x, I get minus f of x, right? And there's just symmetry about the origin, okay, for a sine function. Like the graph has a symmetry about the origin. This is your big one. Okay, so what happens is on an odd function with the Maclaurin polynomial, so even derivatives, oops, that's the derivatives of odd functions are equal to 0. Even derivatives of odd functions are equal to 0. 0 squared to the 4th to the 6th, all these, this is Maclaurin now, not like Taylor. This is only Maclaurin. Okay, so this applies to our Maclaurin. Okay, the Taylor series, you have to evaluate at that specific x value. Okay, so this only applies when a is equal to 0, our Maclaurin. The cosine, like say the cosine of x is an even function, for example. Okay, remember even functions, right? F of minus x is equal to f of x, and then there's a symmetry about y-axis. Right, you can see that if you plot the cosine function, you'll recognize that too. All right, so even functions, this has, we say, oops, so odd derivatives of even functions are equal to 0. So my cosine of the Maclaurin is going to look like this, but it's going to be with even terms. Okay, so let's write out, I'm going to write out the sine function. I can summarize this. So if I take my sine function, right, I'll do this in green so that you know I'm doing it specifically. We're going to start thinking about how I can put this into a summation notation, just so you can start to get accustomed to that. I start at 0 and I go to infinity because it's a series, an infinite series. I've got this alternating positive and negative. So, right, the first term that happens is going to have a positive term. This is going to be x to the 2k plus 1. 2k plus 1 is going to make it an odd exponent. Okay, so the very first term when k equals 0, this is x to the 1, positive x to the 1. And this is all going to be divided by 2k plus 1 factorial. The odd numbers, factorial. Okay, so this is, we're starting to look at, remember I said go out a few more derivatives. We're going to start to think about how I can make this into a formula. You don't have to do this immediately, but start getting into the habit of it because, you know, you will be asked to be able to read these things and to be able to write summation notations as you go along. Okay, so we're going to use, why do we do this stuff? Why do we care? Well, the reason that we do that is because we're going to use these things to help us actually evaluate more complex functions. Like if I look at example number 2, say for example, right, I've got this given 6 times x minus the sine of x as x approaches 0. So as x approaches 0, right, as x approaches 0, that means I'm looking at the Maclaurin, right? That means my a is going to equal to 0. Okay, what polynomial degree best approximates this? Well, you know, if I try to come up with, this isn't so bad, right? I mean, I can probably figure out derivatives for this. It's not going to be so bad. But imagine if this was like, we're going to amp up the complexity of this as we go along. So I'm going to show you this more simple. I think this is like a homework problem, actually. So you'll be able just to copy it right down from your examples. Okay, but what we're going to do is we're going to use substitution. Okay, of Maclaurin series to come up with, let's see, the whole equation. Okay, so we're going to use substitution of, like, say, our sine of x Maclaurin series. Okay, so we call it substitution, but it's also basically like combinations of the Maclaurin to do that. So the first thing that we're going to do is I have to remember my sine of x. Now remember, we're doing Maclaurin. So my sine of x, right, is approximately equal to, it's approximately equal to, let's just copy it down from what we had before, x minus x cubed over 3 factorial. I'm going to do several plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And it, you know, it goes on and on and on. And I can write out the summation notation if I want, but I'll leave it like that. So that's my sine. this here, right, I'm going to substitute in for sine of x in that equation. Okay, so I'm going to take this, substitute into sine of x equation. And we're going to substitute it for the sine of x. So where I see my sine of x, I'm going to substitute in my Maclaurin series. All right, so let's write it out. So it's going to look like, I'm going to do it in pieces, right? So what I'm going to say is I'm going to go x minus the sine of x is going to look like x minus, right? I'm going to substitute in x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and it goes on like that. Okay, now I'm going to distribute the negative, right? So this is going to look like x minus x plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial minus dot, dot, dot. Right, and now I can cancel these. Look, watch, that one goes, right? So x minus sine of x is equal to x cubed over 3 factorial minus x to the 5th over 5 factorial, plus x to the 7th over 7 factorial. Okay. This whole thing, remember our original equation was times 6, right? So now I'm going to go 6 times x minus the sine of x is equal to 6 times, I'm going to plug in this for x times sine of x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, dot, dot, dot. Okay, so now I'm going to distribute the 6 into all those terms. So this is going to become 6 times 6 over 3 factorial, x cubed minus 6 over 5 factorial, x to the 5th plus 6 over 7 factorial, x to the 7th, dot, dot, dot. 6 over 3 factorial is equal to 6. So I'm going to rewrite this as x cubed minus, and I'm going to leave this, I know I can, chunk off and, make it a fraction, but I'm going to leave it as 6 over 5 factorial. You can simplify this even further, right? This is just going to be 6 plus 6 over 7 factorial. This is also, I can simplify this too, but I'm just going to be lazy. Okay, so this is equal to 6x minus the sine of x. So I came up with a Maclaurin, this is the Maclaurin series for this function here. Okay. Oh, and I put my box through it. So this is our Maclaurin series for 6 times x minus sine of x. So I didn't have to do derivatives, right? Or, plug in values or whatever for the whole thing. I could just do this, right? So it's actually much more simple, right? Now they said the question was which value here is gonna work as x gets close to 0. So let's write it out. So when x is close to 0, so you can imagine x is equal to 0.000001. It's getting really close to 0. Then our lowest degree term, x cubed contributes the most to the answer 6x minus the sine of x. So that's the highest, that's the degree term that we're going to use to best approximate it. So to answer the question, 6x minus the sine of x is best approximated by x cubed. That was the question. So how do I represent it as a polynomial? And then how do I do this? You're on the final exam, you'll have some question like this. It won't be an easy problem like 6 times x minus the sine of x. And then once we get here, we're going to be asked to differentiate, take an integral, evaluate it, or whatever. And you're going to be able to do that through the polynomial. Okay. But first we have to learn how do we actually use substitution in order to make that happen. Okay. Let you guys finish writing that and then we'll try another example. Okay. All right. So again, we're going to use substitution, right? So write a Maclaurin polynomial for this, 6 minus x cosine of x squared. So it's similar to what we just did, only look, I'm using x squared term here. Okay, so we're going to write this in steps. So we'll do step 1. The first step is we need to come up with the Maclaurin for the cosine. So the cosine, I don't want to come up with a Maclaurin for this whole function here, right? That's going to be, I could probably do the first derivative, right? I've got the, product rule and the chain rule I need to worry about. But then after the first derivative, my derivatives are really going to explode, right? And especially if I need to go out and do a whole bunch of different polynomials. So substitution is our best bet. So let's write substitution, okay, and combination. So step 1, we're going to find Maclaurin for just the plain cosine of x. Okay, notice it's not cosine of x squared, it's just the plain cosine of x. Okay, and this is Maclaurin, so a is equal to 0. Okay, so we'll do our derivatives. X equals a equals 0 table. Okay, so this is our function is equal to, just remember, we're just doing cosine. Cosine of x, f of 0, cosine of 0 is equal to 1. Our first derivative, let's do a handful of them. So minus the sine, first derivative, minus the sine of 0 is equal to 0. Second derivative, minus the cosine, minus 1. All right, this is equal to sine, positive sine is equal to sine of 0. It's equal to 0. Now, why am I doing this instead of just pulling out the Maclaurin series for it? Because on an exam, we're going to want to see that you understand the process. So go ahead and get in the habit of making this, table for the derivatives and then evaluating that at your a value, whatever your a value is. Maclaurin a is always going to be 0. Let's do our fourth derivative. Right, this is going to be cosine. See how it loops around to the beginning again. So cosine of 0 is equal to 1. Okay, so we're going to get the coefficients. Okay, so I need that part of my coefficient. Okay, and I might as well put over k factorial because that's our whole coefficient. Okay, so let's talk about, it's Maclaurin, right? So I'm going to go f of 0 plus f prime of 0, x to the 1, plus f double prime of 0 divided by 2 factorial, x squared. Remember, we're just doing this to help remind us of what we're trying to do, and then I'll do the fourth. To the fourth, 4 factorial, x to the 4th. Maclaurin plus dot, dot, dot. Maclaurin, remember, is always a is equal to 0, so x minus 0 squared is just x squared. Okay, so let's do this then. So our cosine of x equals, right? Let's plug it in. So this is going to be 1. This is 0. Plus a minus 1. So this is minus x squared all over 2 factorial. The odd is 0. So then plus 4th, this is x to the 4th all over 4 factorial minus dot, dot, dot. So I'll just do out the first several terms like that. Okay, so we have our Maclaurin for cosine. Okay, it seems like, why don't I just pull out the even function when I did before? But let's just get in the habit of doing the derivatives because it's a good habit. So that's step 1. Step 2 that we need to do is we have to plug in x squared into x, right? Because remember, our original question was the cosine of x squared. Well, we just found the cosine of x. So if my cosine of x is equal to this, right, what I'm going to do is I'm going to go x squared is equal to, everywhere I see an x, I plug in an x squared. So I've got a 1 minus, watch this, x squared squared. Don't be fooled that you already have a squared there. X squared is what you're substituting in, plus x squared to the 4th all over 4 factorial. Now it doesn't change my denominator, right? I'm just plugging in a value, x squared, in for x. Okay, so let's multiply this out. So this is going to be 1 minus x squared squared. My rules of exponents are I multiply these together. So this becomes x to the 4th. 2 factorial plus x squared to the 4th, x to the 8th. 4 factorial minus dot, dot, dot. So this is cosine x squared. Okay, so that's our first portion. So we're working our way out from the inside. I looked at my original function. I said, what was the more complicated part? Cosine of x squared. Well, my most basic Maclaurin is cosine of x. So I'm just going to operate on substitution after that. So now my next step is step 3. See how I'm doing all these little portions of my function in bits and pieces. So now I'm going to multiply by x, right? Because my next step was to multiply by x. We'll do the negative separate. So multiply by x, so this becomes x cosine of x squared. Right? So this becomes x minus x to the 5th all over 2 factorial plus x to the 9th all over 4 factorial minus dot, dot, dot. That's x times the cosine. Step 4, we're going to negate. So this is multiply by minus 1. You could have done this multiply by minus x. It didn't matter. I'm breaking this up into like a lot of little steps. Okay, so this becomes minus x cosine of x squared. So I'm going to go minus it's going to look like minus x plus x to the 5th all over 2 factorial minus x to the 9th all over 4 factorial plus dot, dot, dot. Okay, and now I'm going to subtract from 6. Right, so I'm going to go 6 minus x cosine, cosine, I'm running out of space here. Cosine of x squared is going to look like, so I'm going to 6 minus x plus x to the 5th all over 2 factorial minus x to the 9th all over 4 factorial. Right, we're not multiplying by 6. We're just subtracting this whole thing from 6. Okay, and then this becomes our Maclaurin polynomial for that original function that we did up before, that we showed you before. Okay. So far, so good. Substitution, really powerful tool. It's something I guarantee you will see on the final exam. This will be like part A of a question, right? Where you come up with a Maclaurin for a complex function. Part B will be take the derivative. Part C will be take the integral from some number to another number. You know, to try to take the integral of this, right, is going to be a pain. Maybe it's not so bad, but you know, you can imagine a more complicated function, x cosine of e to the x squared, right? Say, for example, that's all plugging things in. And then if I take the integral of just a polynomial, I'm just doing power rule, right? So that's the joy of the polynomial. But you don't want to be coming up with a Maclaurin from this function. The whole point is to use substitution. You just get right to what the answer is by substituting in what the Maclaurin for the basic Maclaurin function, cosine of x, say, for example. Okay. Okay, another example. All right. I think, is this our last example? Yeah, so and then the last page is more of a reference page, but let's do this. So Maclaurin series for f of x equals x sine of minus x. So Maclaurin means our a is equal to 0. We'll keep reiterating that. So our first step is we're going to do derivatives. I know we just did this. I'm just trying to get you guys in the habit. This is x equals a equals 0. So I'm going to go through this more quickly. F of x equals sine of x, right? So this is my basic function is I'm going to do sine of x first, and then I'm going to substitute in minus x. Then I'm going to multiply everything by an x at the end. So f of 0, of x equals sorry, I'm getting ahead of myself. 1. And so I'll do the, we'll go up several. Oh, these are all should be 0. Sorry about that. I'm going fast. Okay, and then so on and so forth. Okay, so this gives us our coefficients, right? So for our sine function, I'm going to use this to help me plug it in. So for sine of x, this is, I should write for sine of x equals. So I'm going to go 0 plus. And then I'm just going to start dropping things off. Okay, so now we get, this is equal to x minus okay. Okay, now I'm going to plug in minus x for x. So I'm going to go TF minus x. So everywhere I see an x, I'm going to plug in a minus x. These all have odd exponents, right? So minus times minus times minus is a minus, right? So that becomes a minus x cubed, minus times minus. So what we're dealing with here is it's going to look like this. Minus x, this sign flips, plus x cubed over 3 factorial, right? This sign flips. This sign flips, that's a factorial. Okay, because it's an odd exponent, so the signs flip. So now our next step is we're going to multiply by x to get x sine of minus x. So I'm going to go, this becomes x TF minus x is going to equal to x times minus x plus so it's going to look like minus x squared plus x to the 4th all over 3 factorial minus x to the 6th all over 5 factorial plus x to the 8th all over 7 factorial minus so on and so forth. So our Maclaurin for x sine of minus x is right here. Okay. It's actually, it seems like, oh, it's a lot of steps and it's a lot of work. It's a lot cheaper and easier than doing derivatives for this. Can you imagine we have the product rule, right, and the chain rule, which is going to accumulate every time we do a derivative, okay? So it's going to make it very complicated. So using substitution on the Maclaurin, and you will be required, we're going to tell you use substitution. So if you don't use substitution and you try to do it all out, you're just not going to have a whole lot of time to do it all out, okay? Okay, let you guys finish writing that. On our last page, I'm going to write down some common Taylor series, some common Maclaurin series for these functions. We're going to find out that these functions are actually equal to their Maclaurin series, but I'm going to write them out on the next page. It's technically notes, but it's important enough that I want to make sure that you guys have it in a format that you can easily access it. Okay, so common Maclaurin series. So the first one we're going to talk about is 1 over 1 minus x. And all of these are infinitely differentiable. Okay, so this looks like 1 plus x squared plus x cubed plus x to the fourth plus so on and so forth. And I'll write what the summation looks like off to the side. But sorry, you can't see that. What the summation looks like off to the side. So that looks like, we'll do, we did k before, k equals 0 to infinity, x to the k. Okay, next one, e to the x. 1. And the next one is cosine. Watch, this is 2 times k factorial, not 2 times k factorial, 2 times k factorial. This is an even function. The Maclaurin is, if you do like a Taylor, it's not necessarily even. Actually, I'll write it both ways. So this is starting at 1, or we can start at 0. Either way is fine. They're the same thing. So this is an odd function. Okay, let me, okay, we're running out of time. Let me do this really quick. So ln 1 plus x, we have just a couple more functions. Be careful, there's no factorial here, and the signs alternate. It looks similar to others, but there's no factorial. And then the last one I'll do inverse tangent. Watch out, there's no factorial either here. So you can see like the sign dominates, but okay. Oh, sorry, you can't see that. All right. So I'll scan this in and put it up online so we have it. Like I said, this isn't really an example. This is really actually technically part of our notes, but it's important enough that I want to make sure that you guys have it in a separate place that's can be easily accessed. Okay. All right. So that's it for 4.2. Go ahead and take a look at the 4.2 homework, but we're not gonna we won't discuss it until Monday. Okay. Remember, it's not on the quiz today, but 4.1 is. Okay, guys. All right. Sorry, I kept you a little bit long. Have a great weekend. Don't forget, homework's due tonight and the quiz opens up at 3 o'clock today. Okay? Take it easy.
Thank you.
Take care, guys.
Thank you.
Bye. Take care.
Thank you.
Thank you.
Bye.